Okay, so this is a BitCam topology seminar, and we are very happy to have Facundo Mémoli. He's from Ohio State University, and today we will hear about the Gromov-Hausdorff distance between spheres. So please take it away, Facundo.
Thank you very much for the invitation. I wanted to use some ideas about estimating and/or computing the precise value of the distance, the Gromov-Hausdorff distance between spheres endowed with geodesic distance. Just a quick recap of the motivation. The Gromov-Hausdorff distance is widely known and used in Riemanian geometry, mostly via its topology. And I think it was introduced by Gromov in the 80s. And perhaps the main theorem that many people know is the so-called Pre-Compactness Theorem proved by Gromov. If you have a positive number d, some dimension parameter m, and then some real number kappa, if you consider a collection f of all Riemanian manifolds which are compact, have dimension m, diameter bounded up above by d, and Ricci curvature bounded below by m-1 kappa, then as a subcollection of the collection of all compact metric spaces, and if you endow M, this collection, with Gromov-Hausdorff distance, then F is totally bounded there. And Gromov-Hausdorff distance is a fairly, say, nice and general notion of it's a metric on collection of metric spaces that has a lot of nice properties. Now, it is also has also been used in shape and data analysis as a notion of the similarity between data sets. And in particular, it's been applied in topological data analysis or applied algebraic topology as a way of expressing what it means for a certain method to be stable. In particular, it has been used to establish stability of persistent homology in the sense that if you compute the Vietoris-Rips barcodes of two spaces, x and y, and if you measure distance between them by something called the bottleneck distance, which is analogous to Hausdorff distance, then Gromov-Hausdorff times 2 upper bounds this distance. And this is actually one of the motivations for this project. In practice, people aim at computing this as a possible bound for Gromov-Hausdorff. And therefore, there's a tension between whatever I can get out of computing this bound and the real value of the distance between spaces. It is known that the right-hand side is not a proper metric, it's only a pseudometric. It can vanish for two spaces that are not isometric. So at any rate, one typically wants to know how strong is a persistent, excuse me, homology invariant. And that leads to understanding what is the baseline. And just to start setting up some notation, let me say that MB is going to denote collection of all bounded metric spaces, and DGH will denote the Gromov-Hausdorff distance, and SM, DM is going to denote each sphere with dimension 0, 1, 2, 3, etc., including infinity. So let me explain the conventions that I make regarding spheres. S0 as a metric space will be the 2-point metric space where the 2 points are at distance pi. SM, to describe SM as a metric space, we think of the usual round embedding of SM into Rn+1. And so we have really, a standard sphere, and then we measure the geodesic distance between points on the sphere, which can be expressed nicely by using inner products and the cosine function. And S infinity, we are also going to deal with S infinity. It's going to be the unit sphere in little L2, again with the same metric. And some direct remarks. The diameter of all spheres, and here diameter means the maximal distance attained by any pair of points on a sphere, is always pi, no matter what m is. And then, of course, if m is smaller than n, the sphere of a smaller dimension isometrically embeds into the sphere of larger dimension. And the problem we want to attack is estimating or calculating all the entries into this infinite matrix containing the pairwise distances in Gromov-Hausdorff sense between spheres. Some basic definitions and properties of the Gromov-Hausdorff distance. And well, and actually I'm going to eventually define Gromov-Hausdorff distance in one way. So if you have sets X and Y, any subset of the Cartesian product between them, R, is a correspondence between X and Y if R surjects onto X and Y via the canonical projections. And we denote by calligraphic R, X, Y, the collection of all correspondences between X and Y. One way to construct a correspondence between X and Y arises when you have a surjection from X to Y. In that case, the graph of that surjection phi is a correspondence, obviously. And another example of a correspondence between two arbitrary sets X and Y is given simply by taking the maximal possible choice here, which is the Cartesian product. And that's always a correspondence. When Y is a single point, then there's only one possible correspondence, which is a product between X and the singleton. Given two bounded metric spaces X and Y, and a relation R, which is non-empty, then the distortion of that relation is defined in this way. You pick two pairs, X, Y, and X prime, Y prime in the relation, and then you measure the distance according to the X between the X projections, and then you do the same for the Y projections. Subtract them, take absolute value, and then look at the worst possible choice, the most pessimistic choice. And in the same way, you can define, well, I mean, if you apply this, you get a notion of distortion for the graph of a function. And this expression somehow simplifies because all the y's that will appear are going to be the form phi x. So you're really taking supremum over x and x prime in x of the difference between the x prime minus the y of phi x prime. And I might just denote that by distortion phi. In particular, when y is a singleton, this term here is going to drop out, it's going to be 0. That's the only metric you can put on a single point, and then distortion x cross singleton will be simply diameter. This whole expression will boil down to the supremum over x and x prime of the distance between x and x prime. Slightly more interesting is a case when you plug into here x cross y. In that case, a distortion of this, let me say, maximal possible correspondence will turn out to be the maximum between diameter of x and diameter of y. And let me quickly show you how this is achieved. It's a simple calculation that I think it's pedagogically useful if you haven't seen the definition of distortion before. Well, let's write first, recall definition of distortion for an arbitrary correspondence. Now, here the pairs x, y, and x prime, y prime are constrained. They cannot be taken outside of the correspondence. But when R is x cross y, the constraint disappears. So in reality, now this term could be anything from 0 to diameter. And the same thing for that term. So therefore, you can upper bound this difference by the max between the two diameters. For example, when you make that choice of x prime, y prime, you obtain diameter x. And when you make that choice, well, sorry, when you make choices so that you produce a 0 and diameter y, you obtain that one. So you could, in practice, in reality, obtain the max of the two numbers. And of course, then you prove that the equality can be attained here, so that you obtain this one. So with these definitions, the Gromov-Hausdorff distance between bounded metric spaces is given by infimizing over all possible correspondences between the two given spaces the distortion of that correspondence. And there's a 1/2 factor that's here for compatibility reasons, historical reasons. And the main properties of the Dgh distance are that, well, first of all, Dgh is a symmetric on the collection of all bounded metric spaces. This means that it satisfies symmetry triangle inequality, and it vanishes if the two spaces are isometric. But there's a stronger, I mean, say the reverse implication is that if they are compact, the two spaces, and distance between them is 0, then they're forced to be isometric. So it's a nice distance, a proper distance. And using what I mean, some of the calculations I described a few minutes ago, the distance between any bounded metric space and the singleton metric space is just equal to 1/2 the diameter of the interesting metric space. And then the distance between any two metric spaces, bounded metric spaces, is always upper bounded by 1/2 the max of the two diameters. Let me skip that one. So again, the question that I want to tell you about today is estimating the entries into this infinite matrix. And I'm going to be referring to that symbol GMN to denote the MN entry into the matrix. And this naturally leads to searching for upper bounds and lower bounds to the Gromov-Hausdorff distance, and to hope that sometimes the lower bound and the upper bound will match. And of course, because of what I said just a minute ago, namely that Dgh is a proper distance, and because spheres of different dimension are really not isometric, we have that GMN is always a positive outside of the diagonal. So here's the first trivial upper bound. It's really simple, but it helps to, so let me say, direct the pursuits that come later. Because diameter of all spheres is always a pi, we obtain this upper bound. All entries into the matrix are upper bounded by pi by 2. Okay, so, and now we would like to have some lower bounds and hopefully try to maybe prove that all distances are pi by 2. That's one possibility. Or maybe try to shrink pi by 2 and reduce it a little bit. So, you know, this is the beginning of the exploration. So the way this happened in my experience and in my own say exploration of the topic was that many years ago I was giving a talk when I was a postdoc, and there were a few colleagues in the audience, and one of them, a topologist, Tigran, he heard me present this, and then he said, but listen, you're dealing with spheres and with correspondences, and correspondences are like functions. They look like functions, only that they may be multi-valued. So it should be possible for you to apply the Borsuk-Ulam theorem, he said. But then my immediate reaction was, well, correspondences are not really functions, but you can fix it. But more importantly, even if you persisted in saying that correspondences are like functions, they are not going to be continuous, and the Borsuk-Ulam theorem requires functions to be continuous in order to be applicable. Anyway, but that thought remained in my mind for quite some time, even though I was unable to make it work for quite some time too. But let's deal with the following, let's say, motto first. The correspondence is like a function. There's a proposition proved in the literature by Carlton and Ostrovsky in the early 2000s that gives an alternative expression for the Gromov-Hausdorff distance that really makes use of functions. So they prove that you can compute Gromov-Hausdorff by restricting yourself to certain special correspondences. So if you have maps now x, a map phi from x to y and a map c from y to x, take the union of the graphs of these two functions and call that R phi c. And then they claim and prove that infimizing over phi and c independently, the distortion of these union of graphs gives you a value which is numerically equal to the one you obtain by not restricting to specific type of correspondences. Namely, the proof like is equal to the original definition of Gromov-Hausdorff. And then if you analyze the distortion of this type of correspondences, remember that you're picking pairs of points. So you can pick the pair of points from here, or 1 and 1. So that leads to the distortion of phi when you pick the 2 points here, distortion of C when you pick them here. And then there's something new that appears that's called co-distortion, when that expresses itself when you pick a point here and a point here. So this is a picture we have. Now we must really think of a maps phi, C that have opposite, say, directions. And so the co-distortion is defined in this way. Distortion is already defined before, but the co-distortion is new. So the freedom in terms of points comes from picking a point x in x and a point y in y. Given the point x in x, you look at the image under phi, and given the point y in y, you look at its image under C. And then you compute this distance between x and C of y, and then you do the same, but now on the y side, and you compute distance between y and phi of x. So you subtract, take absolute value, look at the most pessimistic choice. The interpretation is that co-distortion being small means that phi and C are epsilon inverses of each other. So let me explain what I mean by that. If co-distortion is bounded by epsilon, then that means that this inequality is true for every x in x and y in y. In particular, for example, if I pick y to be phi of x. So if I pick y to be phi of x, then this term will drop out. So I have that dx between little point x and psi of phi of x should be here, is bounded by epsilon. So that's why I say that the identity on x is very close, epsilon close to psi of phi. And then you can obtain something similar here, that identity on y is very close to phi of psi. Anyway, so this is useful actually in TDA when you want to prove things that are of topological flavor, because you can render out of this some sort of, let's say, epsilon homotopies at the simplicial level, and that leads directly into the stability of persistence. At any rate, the maps phi and C are not required to be continuous in any sort of way by the definition of Gromov-Hausdorff. So that still makes Tigran's suggestion a little bit, let me say, difficult to achieve or difficult to implement. Anyway, but still, we looked into this, and I mean, I learned more about the Borsuk-Ulam theorem and the different formulations, and tried to extract some results out of that. So let me tell you what we did with trying to apply Borsuk-Ulam. So Borsuk-Ulam says the following, that for a given n, and you will not be able to find a continuous and antipode preserving map f from Sn into Sn minus 1. So jumping down in dimension and in a continuous manner while preserving antipodality is not possible. And there's an equivalent theorem. These are equivalent in, and that is well known, that it's called the Schreinerman theorem, that says that if you happen to be able to construct a closed cover of Sn consisting of n plus 1 elements, then there must be one of these elements that contains 2 antipodal points. And as a matter of fact, one can directly and immediately apply the Schreinerman to obtain information about the distance between S0 and Sn for any n larger than 1, larger than or equal to 1. Well, here's the idea. So I claim that any phi map from Sn to S0 will have distortion at least pi. Why is that? Well, let's consider UP to be the closure of all the points that map to P under phi. And then UQ, and of course I'm representing S0 by the 2 points P and Q. I just giving them names now. And UQ will be the closure of the set of points in Sn that map to Q. So then UQ is a closed cover of Sm. So by Schreinerman, one of the two contains a pair of antipodal points. So that means that phi x is equal to antipodal points that get mapped to the same point P or Q under phi. So that means that phi x is equal to phi minus x. So that means that the distortion of phi, being the supremum of all possible choices of x and x prime, dominates this number here. But this one is 0 because the points phi x and phi of minus x are mapped to the same point. Therefore, this is pi. And now recall the Carlton and Ostrovsky expression for Gromov-Hausdorff, which was a max of the distortion of phi, distortion of C, and the co-distortion phi C. So I already proved that this one is larger than pi. And of course, we had previously that G0n was bounded by pi by 2. So this concludes that distances must be equal to pi by 2 for every n. And this can be generalized a little bit in the following manner. So if you have any finite metric space with cardinality at most n+1, then any phi mapped from Sn to P must have distortion at least pi. And as a consequence, you have that the Gromov-Hausdorff distance between Sn and any such P is at least pi by 2. The proof is essentially the same as the one that I gave before, only that now we have a general number n here operating. But then this actually leads to an interesting general lower bound for the distance between any two spheres. So if now n is an upper bound for m, then the claim is that GMN is lower bounded by pi by 2 minus the covering radius of Sm with parameter n+1. So this means that you look at the optimal way, the infimal epsilon, that you can use to cover Sm with n+1 balls of radius epsilon. How do we prove this? Well, Gromov-Hausdorff distance satisfies a triangle inequality. So then the distance between Sm and Sn is lower bounded by distance between Sn and P for some finite metric space P to be specified in a minute, minus the distance between Sm and P. But now if I choose P to have cardinality sufficiently small, I will get pi by 2 by the previous slide. And here I still retain P, and then I choose P to be a subset of Sm with a cardinality n+1, realizing this bound. That can be done, so hence we obtain this lower bound here. And let's see how this lower bound fares when we try to interpret the values that it yields. So we know that GMN via that lower bound is lower bounded by pi by 2 minus cov n+1 Sm. If you fix m, then as n goes to infinity, this number will go to 0, right? Because I'm allowing myself to use more and more points to construct covers of a space by taking ball centers at those points. So as n goes to infinity, and if I place a point optimally, then I need a smaller and smaller epsilon to cover this sphere, which is a compact space. So then we learn out of that that the distance actually grows to pi by 2 for any given and fixed m, right? As you move away from the diagonal, you're going to reach pi by 2. Then if we apply that lower bound to the case when m is 1, we obtain something more precise. It's not difficult to prove that the optimal way to cover the circle S1 by a given number, say n+1 of points, consists of placing them as vertices of a regular polygon. And that gives this expression for the covering radius of S1 with n+1 point. And you work out the details, I mean, the lower bound pi by 2 minus pi by n+1, and you get this lower bound for G1n. And again, you see that as n goes to infinity, this converges to pi by 2. But more interestingly, when n is 2, you obtain the lower bound pi by 6, which is at that time when the things got they say explored, this was quite good. I mean, we didn't know anything better than this lower bound, and it was better than the one that you would obtain via persistent homology, for example. Well, say let's say equal to the one you obtain by applying persistent homology. So, and then by using ideas very similar, say also inherited from Luster and Schreinerman, you can prove that, in fact, well, the distance between Gm between Sm and S infinities, pi by 2 for every m. This can be done in a way that is analogous to what I showed you a minute ago. Okay, so to summarize, so far we have that all distances are upper bounded by pi by 2. Then direct application of Luster and Schreinerman tells me that distance between S0 and Sn is pi by 2. Distance between Sm and S infinity is also pi by 2. And then that all entries are lower bounded in this way. And in particular that G12 is lower bounded by pi by 6. One question that is suggested by this pattern here is, could it be that, as a matter of fact, all distances are equal to pi by 2? That would not contradict the information we have here. So we decided to try to answer that question at some point. And for that, we ended up thinking about Borsuk-Ulam again. Borsukulum tells me that I will not be able to find a continuous and antipole preserving map from a sphere to a lower dimensional sphere. But then at some point we realized that we could prove something we can call a reverse Borsuk-Ulam theorem, and which yields a map from a lower dimensional sphere to a higher dimensional sphere, which is surjective, continuous and antipole preserving. And that is a little bit, strange, but it shouldn't be, because what we're doing is we're parameterizing the high dimensional sphere from a small dimensional sphere in a way that retains some structure compatible with spheres, namely that the map is antipole preserving. And notice that there's really no obstacle here, at least no obstacle coming from the standard Borsuk-Ulam, because we are not mapping in that direction. We're mapping from the smaller dimensional sphere to the higher dimensional one. Borsuk-Ulam tells you this is not possible. So, and one immediate corollary of this proposition is that the inequality must be strict. So for all finite m and n, you have you cannot it is not true that the Gromov-Hausdorff distance will be equal to pi by 2. We can produce something smaller than that by using this sort of maps. And here's the idea. So assume that you do fix m and n, and that you apply this proposition and you get a map phi mn continuous surjective and antipole preserving from the smaller dimensional sphere to the higher dimensional sphere. And let's consider R mn to be the graph of this surjection. That will be a correspondence. So then the distortion of this correspondence, well, is being the graph of a map. So I only need to take supremum over x and x prime minus m of this difference. But now the map C being continuous means that I can, well, take maximum here. So have a maximum between dm. This is a distance on the m-dimensional sphere, xx prime minus distance on the n-dimensional sphere between the images. But again, because phi is continuous, there are 2 points, x0 and x0 prime, so that this maximum is attained. And notice that the maximum must be positive, because if not, then we know that 1/2 distortion of Rmn is an upper bound to Gromov-Hausdorff. Gromov-Hausdorff is infimum over all possible correspondences of this number. But if this one is 0, that means that this one is 0. But m is different from n by assumption, right? That would contradict the fact that Gromov-Hausdorff implies that if distance is 0 for 2 compact spaces, and those 2 spaces must be isometric. So that's something we have to remember. The maximum must be positive. Now, there are 3 possibilities that we need to look at. Case 1 is whether x0 could be equal to x0 prime. That cannot be the case, because if x0 was equal to x0 prime, in that case, we will obtain that certainly the maximum is 0. And I just, as I mentioned, that cannot be the case. The other case is that the 2 points are antipodal. If x0 prime is antipodal of x0, then in that case, the distance between x0 and x0 prime is pi. But then also, the distance between the images will be pi, because the map phi mn is antipode preserving. So therefore, the maximum will again be 0. So therefore, distortion is 0. I still contradict that. So that cannot be the case. The final case is, well, the only possibility that remains, that x0 and x0 prime are not equal, but also x0 and x0 prime are not antipodal. So in that case, this entry must be strictly in the open interval 0 to pi. And this one, well, we don't need to do any gymnastics for that. This one will always be between 0 and pi in the closed interval. No matter what, the difference between the 2 numbers will be strictly bounded by pi, and hence leading to the conclusion that all entries into the matrix for finite indices will be strictly bounded by pi by 2. And how do we prove this? Well, the idea is, and here I'm going to discuss in a couple of minutes the main ideas that appear when you try to prove it for m equals to 1 and n equals to 2. So we want to construct a surjection from S1 to S2, which is a continuous and antipode preserving. And C12 is defined by parts, by chunks. So we split S1 into 8 parts, A1, A2, A3, A4, and then they're antipodals. And here they are color-coded so that it is easy to see what's happening. And then in the same way, we also split S2 into 8 parts. And we send, say, green to green, blue to blue, etc. And then we use a space filling curve inside each of the arcs. For example, you see here that there's a curve that is trying to suggest that there's something space filling that's happening. And then we are careful that everything matches up nicely. And the way we extend this to the general case of, say, for example, Sm into Sn is by using spherical suspensions in a geometric sense. But that's just a technicality. So far we have that the distance between M and N in general is upper bounded by pi by 2. The distance between S0 and Sn is pi by 2. The distance between Sm and S infinity is also pi by 2. And then also by applying Schreinerman, we obtain this bound that is more general and softer in a sense, which when instantiated in the case that M is 1 and N is 2 gives me pi by 6. So at some point we started thinking, well, we know this for the case of S1 against S2, and we were trying to close the deal. And by that we mean, could it be that I can find that I can prove an upper bound pi by 6 here, so that I can finally put to rest the question of computing G12. So that leads to asking, of course, I mean, can we find a correspondence between S1 and S2 with distortion 2 times pi by 6? Remember that there's a 2 that allows you to translate between distortion and Gromov-Hausdorff. A few years ago, we managed to construct a correspondence R12 between the circle and the sphere of 2 dimensions with distortion exactly to pi by 3. That led to, of course, pi by 3 here. So we still had a gap, but let me tell you how that correspondence was constructed. So we produced a surjection from S2 into S1 in the following way. First, choose some equator, okay, and then map the equator into S1, just by the identity map, and then divide the top hemisphere, in this case a red part, into 3 equal chunks: V1, V2, and V3. And notice that each of the, well, I mean, this is a V from above. And then in the lower hemisphere, consider the antipodes of each of these regions here. And then we're going to map everything that lives here, say, that will be V1, to that point on S1. That will be the point U1. And then I should say also that U1, U2, and U3 are the vertices of an equilateral triangle inscribed on S1. So then we map V2, anything here, into the point U2, and the same thing for any point in this region V3. We map all those points into U3. And then we antipolarize the map, and we map the corresponding blue parts to the corresponding blue points, and the blue points are the antipodes of each of the red points. And I think that, yeah, that provides like a full description of the map. The map will turn out to be a surjection simply because of the choice that the equator maps through an embedding into S1. And of course, the maps will also be antipode preserving because it's a gluing of several antipode preserving maps.
Yes? Sorry, how do you map the middle 3 edges between V1, V2, V3? Where does it go?
You can make a disjointification, and that it doesn't matter which of the possible maps you choose in the end, but just disjointify in any arbitrary way. And does that answer the question?
Do you want the map to be continuous? You don't care?
No.
Oh, okay.
We don't care, no.
Oh.
Yeah. So this is just any map, and we're going to produce a correspondence out of that map, and then compute the distortion, and the distortion will turn out to be 2 pi by 3, but the map is not required to be continuous.
Oh, okay. So you just care antipodal preserving. Okay.
Yes. But then yes, we proved, we verified, and this is not difficult. One has to do a case-by-case analysis, that the distortion of the graph of this function is 2 pi by 3, thus concluding the claim that G12 is upper bounded by pi by 3. So there's nothing in what I said so far that suggests that this number is actually optimal. All we know up to now is that G12 is sandwiched between pi by 3 and half of that. So it is natural then to try and either construct a better map and reduce this number, or to prove a better lower bound naturally, right? And instead of pi by 6, could it be that the real lower bound should be maybe pi by 3? And we were stuck on at this point for quite some time, and especially we had our results, but the case of S1 against S2 is easy to think about, right? It's very geometric, and we started, let me say, running out of options. And at some point, we went back to what Tigran said. My friend Tigran has said, well, think about Borsukulum. But then Borsukulum really didn't seem to give anything interesting, right? I mean, it just tells me that I cannot find a continuous antipole preserving map from Sn to Sn-1. But the key insight was, after staring at this for a long time, the right question seems to be, well, it might be true that I cannot find a continuous an antipole preserving map like that. But then suppose I do have a map like this, which is antipole preserving from Sn to Sn-1. Then the question is, how discontinuous must that map be? And once we started thinking about that, of course, we had something precise that we could look for in the literature, and we did find it. It was I actually spent a summer reading everything I could about the Borsuk-Ulam theorem, and luckily Matusek had written this book with a very large number of references, and I found one exercise, one asterisk, in a little section of the book, pointing to a paper by Dubins and Schwartz, a paper from 1981, with some version of Borsuk-Ulam applicable to discontinuous functions. So let me tell you what that version says. Suppose you have a map F from a topological space into a metric space. So then you can define the modulus of discontinuity of that function. And that is, I mean, here's the precise definition, but it means something fairly simple. So you pick a point, you look at a tiny entourage of the point, and then you look at how much you break that neighborhood. And you look at the diameter of, you know, the image of this little neighborhood. And the theorem that Dubins and Schwartz proved, and well, this is a corollary to one of their theorems, is that for any map, not necessarily continuous, right? We know that we cannot have a continuous map. So for any map F from Sn to Sn-1, antipole preserving, the modulus of discontinuity of that map has to be lower bounded by some number zeta n-1 that admits a precise formula. And I will explain in a minute what that number is. But here's the formula. Zeta n is the arc cosine of -1 or n+1. And this number is actually the diameter, in a geodesic sense, of the regular geodesic simplex inscribed in Sn. So for example, zeta 1 is 2 pi by 3, being the arc cosine of -1 over 2. And it corresponds to the pairwise distance between well, 3 points corresponding to an equilateral triangle inscribed in S1. Zeta 2 is arc cosine of -1 over 3 and corresponds to the pairwise distance between vertices of a regular tetrahedron inscribed in S2. And notice that as m goes to infinity, zeta m goes down to pi by 2. Okay, so that's what Dubins and Schwartz proved, and I think one possible name for this sort of theorem is a quantitative Borsukulum. And as soon as we understood that statement, then we also understood that the following is true: the distortion of any map between S2 and S1 is lower bounded by the modulus of discontinuity of that map. So then, as an immediate corollary of, well, I mean, the theorem by Dubins and Schwartz, we obtain that the distortion of any map F from S2 to S1, which is antipole preserving, that distortion has to be bounded by 2 pi by 3. So we are not quite there yet in terms of bounding Gromov-Hausdorff, because in Gromov-Hausdorff, you don't really impose any conditions on maps, right? They can be any maps or any correspondences. So the next step was to actually try and massage things to make them work for arbitrary maps. And here's one of the main propositions we found in terms of lower bounds. For any m n and for any m smaller than m, the distortion of any function between Sn and Sm is lower bounded by zeta m. And let me tell you how this is proved. and let's assume that m is 1 and n is equal to 2. So first of all, assume, and the proof is by contradiction. So assume that f is a map with distortion strictly smaller than 2 pi by 3, which is zeta1. So then the trick is to create a new f, which is now antipole preserving and has the same distortion as f. I'm going to tell you in a minute how we might achieve that. But given this f tilde, well, we have that its distortion is upper bounded or equal to the distortion of f, but then the modulus of discontinuity of f tilde is upper bounded by distortion of f by the lemma in the previous slide. And this one is bounded by the distortion of just f. And we assume this one is bounded by zeta1. So then this contradicts the theorem by Dubins and Schwarz. The key part is, of course, how to antipolarize f. And to that, for that, we used the following thing we call a helmet trick. So we decompose S2 as a union of two antipodal and disjoint sets, A and minus A. And it's difficult to really draw it, but here's the way it looks. It looks like a helmet. So you really, first start by taking a hemisphere, and then you start removing parts of a boundary until it really A and minus A become disjoint. So this is a view from below. And here it means, open and closed. And here you took away that part of a boundary, etc. So with such an A, you first consider the restriction of f to A, and that will be f tilde A. And then we define f tilde to be f tilde A on A and minus f tilde A on minus A. And that actually works. And the next step is to prove that the distortions are actually bound, ordered in this manner. And as a corollary of that, we obtain that distance between Sm and Sn is always lower bounded by 1/2 zeta m. And in particular, we also now obtain that G12 is exactly equal to pi by 3 because we had already constructed a correspondence providing this upper bound. So that means that the phi 2,1 that I showed you before is optimal. Okay, so this is a summary of what we have so far. By the reverse Borsukulum, we obtain the strict upper bound pi by 2 for every entry corresponding to finite indices m and n. By the quantitative Borsukulum, we have this lower bound for GMN by 1/2 zeta m, the edge length of a regular simplex inscribed in Sm. And well, we also had these two entries, and then in particular, we were able to prove that via the construction of an explicit surjection between S1 and S2, that for the case of 1, 2, the exact value is pi by 3. So I wanted to make a few comments about the quantitative Borsukulum theorem of Dubins and Schwarz. It appeared in the Pacific Journal of Mathematics in the 80s, 81. As far as I know, it's been cited only 6 times, according to Google Scholar. And the proof relies on the standard Borsukulum theorem, and it's not, it takes several pages. And it was actually, there's some sort of critique to that fact in a paper by Weiss from the late 80s. And Matusek, he suggests a strategy for proving the theorem that we followed and provides a much more succinct presentation of the ideas. And to conclude, I wanted to mention some other results that we obtained that actually provide a precise value for 2 more entries into the GMN matrix. The cases of m equals to 1 and n equals to 3, and then the case of m equals to 2 and n equals to 3. These are supradiagonal. This is a supradiagonal entry, but this one is not. So we already know that well, the lower bound pi by 3 for this distance. That's because G13 is lower bounded by zeta1 divided by 2. And how did we prove the equality? Well, we constructed a correspondence between S1 and S3 with distortion zeta1. In contrast to the correspondence at the optimal correspondence we constructed between S1 and S2, this one was very difficult to find. And the construction is partially motivated by the Hopf map. And you know that was essentially the only map we knew to construct between S1 and S3, and we tried to make it geometric in a sense. So, and I should also say that the construction of what I'm going to call now phi 3.1 will exploit the map phi 2.1 that we constructed before, namely the one that turned out to be optimal between S2 and S1. How does a construction work? Well, imagine that this purple region here is S3. So then pick a point Q on S3. Now, we then assign to this point Q two things. We assign a point P sub Q on S2 and a value alpha Q that tells me how much I have to travel from PQ as a subset of S3 to obtain the point Q. And of course, I mean, what's happening underneath is that we really have one of the rotations that appears when you try to express the Hopf map in coordinates. So alpha Q is really a parameter in that rotation. You rotate this point PQ on the equator of S3 until you reach Q. Now, PQ is a point on S2. So being on S2 means that we know it's we can associate to PQ a point phi 2.1 of P sub Q, where phi 2.1 was the optimal map we knew for between S2 and S1. But then we use this, let me say, vector to move that image by the same amount and through a rotation on S1. So therefore, the final, let me say, result of the construction is that the point Q gets mapped to the point rho alpha Q, and here means rotate according to angle alpha Q, of the image you will obtain by the projection onto S2. Now, this seems very, I mean, you know, a construction for which there may be no intuition that I can give you right away, but we did, this was an insight that came at some point that we should try something like this. We tried it, and then eventually we verified that the distortion of this map is actually to pi by 3. And the verification is leads to contemplating a very tedious case-by-case analysis. And another result that we obtained hinges on the construction of a optimal correspondence between S2 and S3, namely a correspondence for which the distortion is that value. And this correspondence is one that was structurally very different from the ones that the other two that we constructed. And in the end, this is a figure that hopes to summarize what we know and what we don't know related to the matrix G. So the green entries are fully known, and the orange entries are also known. This corresponds to S0 and S infinity. And then the purple entries are partially known. We know some lower bound, zeta m. Zeta m, remember, is the side length of the M geodesic simplex. And there's an upper bound that I didn't have time to describe, but we also have some upper bound that in general doesn't match zeta m. And there are some questions that are motivated by some of the things we did manage to prove. the main conjecture we have is that, as a matter of fact, on this line here, on this principal diagonal, the values that really take place are these. And we know that to be true already for, well, this one, this one, this one. There are some other auxiliary, or say smaller questions that we wrote into this preprint. And I mean, for example, here's one I don't know how to answer, but is it true that if I fix an M, then the values monotonically increase from left to right? That hopefully, I mean, that seems that should be true, but we don't have yet an understanding of that. I wanted to mention that also with Colorado State and Carnegie Mellon, we are running a polymath project related to these sort of questions. And that's with colleagues Henry Adam and Florian Frick. And we have actually improved some of the lower bound that the lower bound that I showed you today. And the sort of exploration also suggests maybe trying to approach the calculation of Gromov-Hausdorff distance for other spaces with simple and homogeneous structure beyond spheres. Thank you.
Okay, thank you very much, Facundo. So any questions from the audience? Or comments? Oh, okay, maybe I can ask about the so at the starting of your talk you mentioned the bottleneck distance, and for which the distances that you talked about, the Gromov-Hausdorff distance, it gives an upper bound. So is it does it give you optimal upper bound in the case of spheres, or in
let me, yeah, I think I can say a few things about that. Thanks for the question. I possibly have some. Right. So what happened, and this is something I said in the end to not mention, but this is a lower bound we obtain for Gromov-Hausdorff distance based on bottleneck. Okay. And for spheres, the lower bound is 1/2 of the one that you obtain via Dubins and Schwarz. That is what ended up happening. So I'll write it here. So and this one turns out to be 1/4 of zeta m here, assume, which is not so good because I can directly prove the 1/2 by Dubins and Schwarz. And here there's a calculation that has to be done. So that is the succinct answer. Is not optimal, and that was a disappointment, frankly, because we spent a lot of time working on the stability question and trying to figure out how to compute the barcode, etc. Right? And it's interesting that one thing that matters here is that the fundamental class of SM actually induces an element of DGM M of SM. And the way we get to estimate this number is by actually understanding how long this fundamental class actually lives through the filtration. And that's what led to the filling radius of SM. And essentially proving that the filling radius of SM always yields an element of the barcode of SM. And then that Katz had actually computed this filling radius, and filling radius, well, twice filling radius is actually equal to Zm. That is what provides a connection with Dubin and Schwarz, but however, the techniques do not yield an optimal coefficient here. For some reason, we found this at 1/2, and we could not get rid of it. Well, this 1/2 relative to this one. Right? So there's a 1/4. The optimal is 1/2 in general.
Okay. Okay. Thank you. Any other questions for Facundo? Okay, so if not, let's thank you again. So it was great. Thank you very much. Great talk.
Thank you very much for the invitation.